Okay, so we left off with the this net ionic equation here. So let's go ahead and get back to this. Now we need to talk about the activity series, which we talked about this a little bit last year. And again, last year, before we were really talking too much about the net ionic or anything like that, the activity series is somewhat useful in the sense that it will tell you which elements are most reactive. So the way that this works is you basically have lithium highest on the activity series. It is the one that is most likely to be oxidized. Okay, so you can see over here, maybe you can see this, ease of oxidation increases as you go up. Okay, so it's much easier to get an electron to come off of the lithium than it is pretty much anything else on this list. Okay, and these are just the common ones that are on here. This is not obviously every metal, but of the common ones, lithium is the one that it's easiest to get the electron away from, and so that means that it's kind of the most reactive. Okay, if you find it in nature, lithium is the one that is most likely to give its electron away to something else and become Li+. Okay. And so you're not going to find lithium uncombined in nature very much. Same with potassium, the ones at the top of this list. Now you get down here to gold, okay? Gold is not very active. In other words, it doesn't really like to give its electrons away. So it's hard to oxidize it. In other words, it's hard to take its electrons away from it. And so that's why you find a lot of gold uncombined in nature. It's not that reactive, okay? And just as a reference point, kind of shows where hydrogen is and all of this. The reason that they put hydrogen in there is because when you have an acid like HCl, then you can see if the metal will replace the hydrogen or not in that compound. Anything up here will replace hydrogen. Anything below it will not. So you put a metal, one of these metals at the top here, into an acid, it's going to react. But if you put copper, silver, mercury, platinum, or gold into acid, it's typically not going to react. Okay, so that's the idea behind the activity series. It tells how active a metal is, and again, metal high on the list is easily oxidized. And again, Leo, lose electrons, oxidation. Okay, and then a metal that's low on the list is not easily oxidized. Now you're not really going to need the activity series for the AP chemistry exam, so we're not going to talk about it a lot in this class. And there's two reasons. I'm going to give you, and I should have done this in the first place, but I didn't. I think I just gave you a periodic table. On the AP exam, on the back of that periodic table, there is a reduction potential chart. Okay, and the reduction potential chart is basically the activity series in reverse. So if you learn how to read that right, then you don't need the activity series. So that's one reason. The other reason, though, is there are not going to be any do not reacts on the AP exam, as we already talked about, which means if they give you a single replacement reaction, it's going to happen. So they're giving you one that will work. They're not trying to trick you, okay? So this is really important, but this is one of the main reasons you don't need the activity series for the equation writing portion of the AP exam, because they're always going to give you equations that work, okay? Now, having said that, on the Ultimate Chemical Equations worksheet, there are going to be some that don't work because they want you to just practice looking at the activity series. And this one may or may not work. So here's our sample problem. Will an aqueous solution of iron 2 chloride oxidized magnesium metal? All right. So the equation for this, if we're just setting this up, it would be Mg, magnesium metal is the solid, and then we've got a solution of iron 2 chloride, so that's going to be FeCl2. And what we want to know here is, can the magnesium replace the iron? Is it more active than the iron? So let's go back here for a minute, look at our activity series. Here's magnesium, here's iron. Okay, magnesium is higher up on the chart, so it is going to be more easily oxidized, which means it will give up its electrons to the iron. So we're going to end up with MgCl2 here, and the iron's going to get replaced. It's going to end up being by itself as a solid. Okay, now that's the molecular equation. That's not balanced yet. Is it? No, it is, because we've got FeCl2 and MgCl2. Alright, so it's already balanced, which is nice. Then we need to write the net ionic for the equation. So we've got Mg solid plus Fe2 plus 2 Cl minus ions when that splits apart. And that gives us Mg2 plus again 2 Cl minus ions plus Fe solid. Okay? And you can probably see here the only thing that doesn't change, the spectator, is the chlorine, so let's get rid of that. That gives us solid magnesium plus Fe2 goes to Mg2 plus Fe solid. Okay? And again, what's happening there is the magnesium is going from a 0 oxidation state to a 2 plus oxidation state, which means that it's getting oxidized. Lose electrons, oxidation. Okay, it's becoming more positive. The Fe2 plus is changing to Fe solid. That's going from a 2 plus to a 0. Must be gaining electrons to do that, so that means it's reduction. It's being reduced. Okay? And so that's an oxidation reduction reaction. Okay, we'll talk about solution concentrations next time. Hopefully that makes sense. I don't think there's a lot new there, but the oxidation reduction idea is a little bit new. So we'll practice on this for a couple of days in class to make sure you guys have it. All right, that's it.